The Apollo 11 moon landing was not a triumph of flawless engineering. It was a series of miraculous escapes from certain death that the world was never supposed to see. While 600 million people watched a perfect mission on their flickering TVs, they had no idea that Neil Armstrong and Buzz Aldrin were essentially riding a controlled explosion held together by duct-tape logic and last-minute prayers. Behind the grainy footage lies a story of 400,000 minds fighting a silent war against physics. This is Astro Trivia, and today we're stripping away the myth to reveal the terrifying science that nearly turned humanity's greatest leap into its most public tragedy. The mission almost ended before the engines even ignited. Just hours before launch, technicians discovered a leaking hydrogen replenish valve 200 feet up in the Saturn V's third stage. Liquid hydrogen is kept at a bone-chilling -252 degrees Celsius. It boils off constantly, requiring a steady top-off to keep the tanks at 100% capacity. Without a full tank, the rocket couldn't perform the translunar injection, the literal shove needed to reach the moon. The leak was a ticking bomb, capable of turning the entire launch pad into a crater. With the clock ticking and the astronauts already boarding 100 feet above, a three-man suicide squad of technicians was dispatched. They tried tightening the bolts manually, but the leak persisted. In an act of pure desperation, they grabbed water from an eyewash station and poured it over the valve. The water froze instantly, creating an ice seal that stopped the leak but rendered the valve useless. To keep the rocket flight ready, engineers had to manually toggle the main fill valve, a component never intended for that purpose, until the final seconds of the countdown. But the danger wasn't just outside the craft, it was in the very air the astronauts breathed. To save weight, NASA filled the cabin with pure oxygen at low pressure. However, after the horrific Apollo 1 fire that killed 3 astronauts on the pad, the team had to rethink everything. Oxygen is violently flammable. For the Apollo 11 launch, they compromised with a 60% oxygen and 40% nitrogen mix at a high pressure of 16 psi. This created a new biological nightmare, decompression sickness, or the bends. At sea level, our blood is saturated with nitrogen. If the cabin pressure dropped too quickly during ascent, that nitrogen would form lethal bubbles in the astronauts' joints and brains. To survive, Armstrong, Aldrin, and Collins had to undergo a pre-breathe for 2 hours before launch, inhaling pure oxygen to flush every trace of nitrogen from their veins. Those portable suitcases you see them carrying to the van, those weren't for style. They were life support units pumping pure oxygen to ensure their blood wouldn't boil the moment they left Earth's atmosphere. Having cheated fire and physics on the ground, they were finally cleared for the most dangerous journey in human history. Escaping Earth's atmosphere was only the first impossible hurdle. Now, Apollo 11 had to navigate a literal minefield of radiation invisible to the naked eye, the Van Allen belts. Imagine 2 massive donut-shaped rings of highly charged lethal particles trapped by Earth's magnetic field. In the 1960s, the true lethality of these belts was a terrifying unknown. Plunging straight through the densest regions would have subjected the astronauts to a fatal dose of radiation, turning their spacecraft into a high-speed microwave oven. Traditional lead shielding was entirely out of the question. It would make the Saturn V far too heavy to ever leave the launch pad, so NASA had to cheat geometry. Relying on the brilliant, unsung human computers, the pioneering female mathematicians who calculated orbital mechanics by hand, NASA developed a slanted flight path. Instead of blasting straight through the deadly horns of the inner radiation belt, the spacecraft's trajectory was aggressively angled to thread the cosmic needle. They bypassed the highly concentrated lethal zones entirely, carefully slipping through the much weaker, safer fringes of the outer belt. But dodging radiation meant absolutely nothing if they missed their target. To break free of low Earth orbit, the crew had to execute the Translunar injection, or TLI. This required the Saturn V's third-stage engine to ignite for exactly 5 minutes and 48 seconds, adding precisely 10,000 feet per second to the spacecraft's velocity. The margin for error was virtually zero. If the burn was a mere second too short, they would fail to escape Earth's gravity and eventually crash back down. A second too long, and they would blow right past the moon, hurtling into a permanent, inescapable orbit around the sun with no hope of rescue. To hedge their bets against a catastrophic engine failure in the lethal void of deep space, those same mathematical geniuses employed a brilliant cosmic failsafe known as the free return trajectory. Rather than burning precious fuel the entire way, Apollo 11 essentially coasted like a thrown baseball. They aimed not for where the moon was, but exactly where it would be in 3 days' time. They flew a massive figure-8 path that weaponized the moon's own immense mass. If their main service propulsion engine died and left them completely stranded, this mathematical safety net guaranteed that the moon's gravitational pull would act as a giant cosmic slingshot. It would whip the dead spacecraft around the dark side and hurl it naturally back toward a splashdown in the Earth's Pacific Ocean. It was the ultimate gravitational insurance policy. Once safely on their coast toward the moon, the astronauts had to perform a terrifying mid-space construction project. The Apollo spacecraft wasn't a single ship, but a 3-part stack. The fragile lunar module was safely tucked away inside a protective garage on top of the spent third-stage rocket. To access it, Command Module pilot Michael Collins had to detach his ship, use tiny thrusters to manually flip it 180 degrees in the pitch-black vacuum, and perform a flawless nose-to-nose docking to extract the lander. One wrong tap of the controls could have smashed the delicate lunar module to pieces. With the ship fully assembled, their lives now depended on the Apollo Guidance Computer, or AGC. By today's standards, its specs are laughably primitive. It possessed a mere 4 kilobytes of erasable RAM and about 72 kilobytes of rope memory, software that was literally woven together by textile workers in Massachusetts using copper wire. Yet this briefcase-sized marvel was the first computer to use silicon-integrated circuits, paving the way for the modern smartphone. It tracked the ship's orientation using an inertial measurement unit, a sophisticated gyroscope system acting as the spacecraft's inner ear. However, 1960s gyroscopes weren't perfect. Over time, tiny mechanical frictions caused drift, meaning the computer's internal map would slowly lose its alignment with physical reality. To fix this, NASA turned to a technology older than the United States itself. Just like 18th century sailors navigating the high seas, Michael Collins used a specialized space sextant. He would peer through the optics, locate specific guide stars from a catalog, and measure their exact angle against the Earth's horizon. He then fed this raw data back into the AGC to manually recalibrate the gyros. But navigating the featureless void brought a new immediate threat: severe thermal shock. In the vacuum of space, there is no air to circulate heat. The side of Apollo 11 facing the sun baked at a blistering 250 degrees Fahrenheit, while the side cloaked in shadow plummeted to minus 250 degrees. This extreme gradient would have warped the spacecraft's metal hull, frozen vital fuel lines, and completely fried the primitive electronics. The solution was surprisingly low-tech. Engineers implemented passive thermal control, affectionately dubbed the barbecue roll. The astronauts set the spacecraft into a continuous rhythmic spin, rotating exactly 3 times per hour. Just like roasting a rotisserie chicken over a campfire, this constant motion ensured no single side was overexposed to the extreme highs or lows, keeping the internal cabin at a perfectly steady, comfortable room temperature. Leaving the protective cocoon of Earth's magnetic field meant entering a cosmic shooting gallery. Deep space is flooded with high-energy galactic cosmic rays and unpredictable solar flares that can shred human DNA and scramble primitive computer circuits. A lead-lined ship would be far too heavy to fly. So NASA made a terrifying, counterintuitive gamble. They deliberately scheduled the Apollo program during a solar maximum, the absolute peak of the sun's violent 11-year cycle. Why? Because the intensified solar wind created a massive magnetic umbrella, a strengthened heliosphere that pushed away the much deadlier, harder-to-block galactic cosmic rays. By accepting the risk of solar flares, they traded certain slow radiation poisoning for a risk they could monitor. To survive the sun's sudden outbursts, NASA relied on a global ring of observatories staring at the sun 24/7, ready to warn the crew to dive into the most shielded corner of the command module. But this delicate survival dance required a flawless, unbroken lifeline to mission control. In 1969, there was no internet, no fiber optics, and no global satellite network. To bridge the 240,000-mile gap, engineers developed the unified S-band system. Instead of juggling separate radios for voice, grainy television video, and critical spacecraft health data, they combined it all into one single high-frequency stream. To catch these faint, ghostly whispers from the cosmic void, NASA cast a massive net across the globe. They built 17 ground stations from Madrid to Canberra, deployed ships in the vast oceans, and flew specialized aircraft to catch signals where land couldn't reach. Yet even this unprecedented web of technology had a chilling blind spot. Every time Apollo 11 slipped behind the far side of the moon, the massive lunar body blocked every single radio wave. For 48 agonizing minutes during each orbit, the three men were utterly cut off from the human race. If their engine failed to fire, or if a rogue meteorite pierced the hull in that shadow, mission control would hear nothing but static. In those moments of total blackout, they were the most isolated human beings to ever exist, forced to trust their fragile, hand-woven machinery in the absolute silence of the void. That crushing isolation was just the prelude to the most dangerous 12 minutes in aviation history, the descent. Nobody actually knew what the lunar surface was made of. Some of the brightest scientific minds, like astrophysicist Thomas Gold, pushed the terrifying fairy castle theory. They believed billions of years of micrometeorite impacts had pulverized the moon's surface into an incredibly fine, electrostatically charged dust. Gold warned that this dust structure was so porous that the 15-ton lunar module would simply sink into it like a stone dropped in an ocean, burying Neil Armstrong and Buzz Aldrin alive under a miles-deep sea of powder. Because NASA couldn't entirely disprove this nightmare scenario, they over-engineered the lander. They gave the Eagle a wide splayed stance with crushable honeycomb aluminum shock absorbers inside the legs to prevent tipping. They equipped it with massive 37-inch circular footpads, essentially giant space snowshoes, to distribute its weight over the unknown dust. Dangling beneath 3 of these pads were 68-inch blue sensory probes. The instant a probe brushed the soil, a lunar contact light flashed in the cabin, signaling Armstrong to immediately kill the engine. If he didn't, the exhaust pressure bouncing off the ground could blow the ship apart or carve a deadly, unstable crater right beneath them. As Eagle plummeted toward the Sea of Tranquility, chaos erupted. They were coming in too fast, passing landmarks seconds ahead of schedule due to residual pressure in the docking tunnel, giving them an extra shove. Then the master alarm blared. It was the infamous 1202 program alarm. A faulty radar switch was flooding the Apollo guidance computer with useless data, maxing out its memory and forcing it to reboot mid-descent. In Houston, a 26-year-old controller named Steve Bales had mere seconds to decide if they should abort. Trusting the software's genius priority architecture, he gave the go. But the computer was steering them directly into a massive crater filled with jagged, car-sized rocks. Landing there meant tipping over, ripping a hole in the hull, and making launch back to orbit impossible. With ice in his veins, Armstrong took manual control, pitching the craft forward to skim over the boulders. As he hunted for a flat patch, the fuel gauge triggered a low-level warning. Houston called out 60 seconds, then 30 seconds. With blinding moon dust kicking up and obscuring his vision, Armstrong was flying blind. Finally, the blue contact light illuminated. The Eagle slammed into the dust with barely 25 seconds of fuel remaining. Against all odds, they had survived. That smooth, historic touchdown wasn't just the triumph of 3 brave men. It was the absolute pinnacle of collective human genius. Hundreds of thousands of unsung engineers, mathematicians, and technicians fought a relentless, silent war against the unforgiving physics of deep space, weaving millions of brilliant failsafes to bring them safely home. The Apollo 11 mission wasn't a miracle, it was a masterpiece of human defiance. If you loved uncovering these hidden secrets of the universe, hit that like button, subscribe to Astro Trivia, and share this video with your friends. We have plenty more deep space mysteries coming.